keep this flow chart going. I'm realizing now what I should have done was had the flow chart been a part of the exam, but whatever. I'll do that next time. The next group of victims. So, and Di, this goes up to a question you just asked me 10 minutes ago, not even 10 minutes ago. So, if anybody wants the flow chart, let me know. I'll give it to you. Okay. It is what it is. It is something I want to expound upon. Oh, what you got? Oh, for sure. You send me an email. I'll send it to you. Because it's not quite done yet. There will be one more branch of the flow chart that I'm going to add, but I'll send you guys the full flow chart so you have the whole thing. And it's an Excel spreadsheet. You just pop it open. And basically, with this, I've designed the flow chart for you to take with you. It's not so much to make you pass this course, because there's no reason to memorize anything in this course. Everything's done in a class. You take your time, you work through it, you use resources at your disposal. This is kind of designed to answer. I got an email from a student just yesterday from a couple 244s back. She said, I'm forgetting so much already. I forget what to do when. I'm like, here. And I sent her the flow chart. She's like, oh God, that's what I needed. I needed that to know when I'm sitting in my desk at my job and I've got data, what to do with the data. That's what this is for. It's for you guys to take with you as a reminder. And these exist online, but this is just, you know, the one I made up. So basically, this is what she needed. She needed to know what to do based on certain parameters. And it's just a way of flow charting through. So if you look at where we've been, this was confidence intervals, estimating parameters, figuring out how big something is, which is also in that blood doping talk from yesterday. Estimating parameters. And then seeing if a parameter has changed. So you've got an estimate or a value you already believe exists. Has it changed from that due to some kind of a constraint, i.e. sticking EPO in your blood? So, and then you go, okay, so this is where we're at smack dab in. Which one are we testing? Well, we've been flip-flopping back between percentages and averages, trying to do a little bit of both. And hopefully after this weekend, I'm going to have more data for you guys, because I have new brakes to put on my crossplate, and I have the same old tires. I'm going to have a little Nova for us on Tuesday, hopefully, if I can get the data collected this weekend. Max will be excited. So which one? Proportions or averages? And then how many of them? Are you doing one? Are you doing two? This is what we were doing, and there's quizzes posted. I guess you did it for this week, if you did quizzes for this week. I'm not sure if anybody did. But this right here was one of the quizzes that was for this week. And this right here was the other quiz for this week. If you did, you might not have done them at all. Some people are just doing in-class quizzes now, and that's totally fine too. So if you have one, including match pairs, or two, one or two, Di, this was your question. You use the Z's for one or two proportions. You use the T's for one or two samples. What changed is what happens when it goes to more than just two. So we'll deal with the averages on Tuesday. That'll be the last thing we do in this class, dealing with more than two averages at a time. But for proportions, when you have three or more, like the iPod randomizer, we have 10 songs randomizing through. M&Ms, we have exclusive tank. M&Ms, we have 6 colors that we're going to be randomizing through. Blood doping, we have 3 different levels of hemoglobin that we're going to be talking about. Those are more than 2, right? 3 or more. You can't use the Z-curve anymore because the Z-curve requires no more than 2 variables to compare directly. If you have more than 2, you can't subtract, look for a difference, and then peg where the difference is. If you have 2 numbers and you subtract them, blah minus blah, and it's a positive number, well, you know the first one was bigger than the second one. If you subtract them and they're negative, you know the first one was smaller than the second one. If you subtract them and they're 0, you know they were equal. But if you subtract 3 numbers and that's positive, you don't know which ones or which one is or are bigger than the other or others. Ooh, a weird sentence. I think it was grammatically correct. Right, that's the question. Too many question marks. So that's where goodness of fit comes in, and that's where that chi-square distribution came in. Why do we call it goodness of fit? Do you remember? Goodness of fit. What's fitting good? Oh. No, I'm going to say it though. What's fitting good? Oh, it's Catholic school. It hurts to say. What are we testing the goodness of? The goodness of fit of what? Data 2 and good. You're completely correct. I'll give you a hint. We're testing the fit of data. Yes, 100% correct. What are we comparing the goodness of fit to? Yes, an expected distribution. We're testing an expected distribution against the observed sampling distribution. That's exactly right, Dad. So we got data, and that data has a distribution. We also have an expected distribution that we think the data is coming from, and we want to see how well they fit each other. If you think about it, it's just like every other hypothesis test. You've got a null hypothesis that has an expected belief. And then you've got data, and the data either agrees with that or doesn't appear to agree with that. And a goodness of fit gives you the newest way to measure that. So we're going to start today by looking at M&Ms, milk chocolate M&Ms. I'm going to hand these around to you. There's 4 bags left. This is from last term. There's 3 bags left in here. Go ahead and grab those first. And then here's another box. You crack this one open and grab a bag out of there.
Are we going to turn any of these in?
This one I think we'll turn in today. We're only going to do one test today. It's the M&M test. Because it takes a while to collect the data and then crunch it. So I think we'll turn in... Oh, we done that? Chill. So, yeah, we'll turn this one in for sure. And then we'll turn in... There's one more you have. So I think we'll have 2 more in class. And then everything else will be posted. It's week 9. We said that earlier. I didn't think about it myself. 16 or 17, I believe. So, I want to go back to Di's question. The question is, okay, so you're all getting a bag of M&Ms. And what I want us all to do, you can go ahead and crack them open if you want. Don't eat them just yet. Because I want to count the colors that you have first. And I want to compare what we get to what? Expected. Now the question is, what is the expected? What is the expected? Well, here, this is what Mars tells me. This is what, whoops. Yeah, well, actually, they have it posted on their website. I didn't have to write to them. I write to them later. We'll get back to that. So if you look, oops, let's back up 1. Here we go. These are the distributions that Mars popularizes. Now, if you look at some of these, they're going to vary. These are the pie charts of certain people doing this experiment as well. But their exact color distribution I have written down somewhere. I think we'll look for it. I'm going to put it on the board. Mars tells me one of these is, a lot of these are the, no, that's the big one. I got it in the spreadsheet, or in the notebook. They tell me that each of the colors has a percentage.